when we graphed all of those functions, if I have a circle tangent to the graph,
it actually is.
would touch once. If I have this curve, a tangent to the graph touches once. Now this one's actually kind of special. Because what's going on with this tangent graph?
It's a parabola.
Not the curve is fine. But what's going on right here?
Touches once.
Touches once, that's what makes it tangent. But what makes it special? It's because it is
Flat.
horizontal.
Yes.
Alright, it's horizontal. So what kind of slope does the horizontal have?
0.
0. Okay, so that one's actually going to be special. Now, this one. You see how it only touches once, even though it kind of goes through. This one also touches once, even though eventually it actually goes through again.
Yes.
Alright, but the point of tangency, it touches once here. That's
Yes.
what we're going to be talking for the next couple chapters, is this tangent. I get functions that look something like that. Now, this one right here is our original cubic function. This right here was x minus 5, 2x minus 5, and 3x minus 5. Which one looks like it's at a point of tangency at 0, -5? Which one looks like it? Is it the x minus 5? Is it the 2x minus 5? Is it the 3x minus 5? Which one looks like it has a tangency? What? X minus 5? That one? That's the one you think? So it just touches once? Which one looks like it only touches one single time? What?
The x
You think the x minus 5 too?
Yeah. X minus 5.
Yeah. All right. So, recall our slope of our secant line. Okay, we did this one last chapter. So we have y2 minus y1 over x2 minus x1, basically, right? But what's going on at the bottom? Guess what happens to our c's? They cancel. They cancel. So the slope of my secant line ends up being f of c plus delta x minus f of c all over delta x. All right? So that is actually our equation for when we find a slope of a secant line. Now we're going to take that and we're going to put a limit statement on it. And so we're going to take that same exact thing, but now I'm going to say my limit as x approaches 0 of this. I'd like you to write this down. This is where we're going to be at the next couple days. So the limit as delta x approaches 0 of f of c plus delta x minus f of c all over delta x.
Wait, I can't hold it.
So what this is going to be doing is actually finding the slope of a tangent line. All right, and this is extremely important in our mathematics. So what's really happening behind the scenes is what's going on is our delta x is approaching 0. What that means is delta x is the width of x. All right? And so what we're doing is we're taking this delta x and we're getting closer and closer to where I want the slope to be until I get to 0.
And
Because that's what our limit as delta x approaches 0 is. All right? So let's memorize this. Let's be able to use it. So we have a limit as delta x approaches 0 of f of c plus delta x minus f of c all over delta x. You're going to have to memorize that. Okay? All right, let's use it. So we're going to find the slope of this graph of 2x minus 3. And so we're going to utilize our little slope formula. So I have a limit as delta x approaches 0. And now all I do is substitute in c plus delta x in right there. So now I end up having 2 times c plus delta x, and then minus 3, because that's the rest of my function,
yes.
and then minus
Wait.
and then minus my 2 times, now I'm going to substitute in c,
Wait.
and then minus 3. all over delta x. And so now we just need to simplify this up a little bit. So we're going to distribute the 2. All right. So let's just distribute the 2. So now I end up with 2c plus 2 delta x. Then I still have minus 3. And now I need to distribute this negative. So now I have minus 2c. And now I have
Oh,
plus
I've already
3
got it.
all over delta x, as my limit as delta x approaches 0. Now, some lovely things should happen here. What happens? 2 c's cancel. Love it.
Yes. And the 3's cancel.
The 3's cancel. Love it. Anything else?
Delta x cancels and leaves you with 2.
The delta x's cancel as well. So now I have a limit as delta x approaches 0 of 2. So it's going to be what? 2.
And that is going to be true.
So
for
this,
every last one.
exactly. So
That's
the
going to be true
slope
for
of a
every-
tangent,
That's going to be true for every point on the graph.
exactly.
So that's
So the slope of the point 2, 1 is going to be what? Is 2. And the slope of everything is actually going to be what?
2.
2. We didn't have to do any work on this one. Because guess what? This was a what?
Linear.
A linear line. It was
Yes.
a y equals mx plus b, right?
Yes.
What's my slope of this one? 2. Now, did we prove it mathematically?
Yes.
Yes. Am I going to ask you to do that a couple times on your homework today? Yes. But everywhere is going to be a slope of 2. All right? All right, let's do the next one. So now I have the equation x squared plus 1. Now I'm going to find the slope of the equation x squared plus 1. Now, is this one linear?
Nope.
No.
No.
So I'm going to have to use a little bit of my slope formula. All right. So let's substitute in. So now I have a limit as delta x approaches 0. And now I substitute in c plus delta x, quantity squared, plus 1, and then minus. Now I substitute in c. So now I have c squared plus 1 all over delta x. So in that first part, I need to FOIL. So what is c plus delta x, quantity squared? C squared plus
2 delta x.
2c delta x, and then plus
Delta x squared.
delta x quantity squared. All right, so that's what that FOILs to. And then I still have plus 1, and now when I distribute this negative, I end up with minus c squared, and then minus 1, all over delta x. So now I have a limit as delta x approaches 0 there.
And something happens. And it happens again.
Now, some lovely things should cancel here. So what cancels?
All ones cancel.
My c squareds cancel. What else cancels?
The ones.
The 1s cancel. What else cancels? Some delta x's. So I'm going to distribute dividing by delta x. So this one goes away, and then this one goes to a degree of 1. So right now I'm left with the limit as delta x approaches 0 of 2c plus delta x. Now, what do I substitute in? 0. I substitute in 0 for delta x. And so when I substitute in 0, now I get what? 2c. All right. And so my slope equation is 2c. But I want to talk about at the points 0, 1 and 1 or negative 1, 2. So I want to find the slope at 0, 1. So I substitute in my x coordinate in for this. So I substitute 0 in.
0.
So 2 times 0 is 0. And now I want to find my slope at negative 1, 2. So now I substitute a negative 1 and I end up with
-2.
negative 2. Now, there's my function. This x squared plus 1 is my function.
And those are derivatives.
My slope equation is at 2c. All right? So anything that I substitute in my equation of 2c, that's going to give me the slope of that function, or the slope of the tangent line of that function. So for instance, at 0, 1, guess what kind of slope I have? I have a 0 slope, a horizontal slope. At negative 1, guess what I have? I have a negative 2 slope. What if I wanted it at 3? What would be my slope at x equals 3? It'd be 6.
Yes.
All right? Isn't that pretty powerful?
Yeah.
All right? So there's my equation of my slope for my tangent lines.
And
All right.
and then I keep going to
There we go. 1 through 10.